Hello everyone, my name is Sergey Mashchenko. I am from SharkNet Computer Ontario Alliance and I'm also based at McMaster University. Today I will be talking about debugging your code with DDT. Here's the outline. I will start with a brief overview of DDT. I will talk then about using DDT on national systems. And then I will show you how to debug with DDT using a live demonstration. I will cover basic DDT features, and I will also show you the typical code situations you encounter when you need to debug your code, such as serial code debugging, C, C++, Fortran, Python, OpenMP multi-threaded debugging, MPI, GPU, CUDA or ROCm, heap. And at the end, I will cover some of the advanced features of DDT, and there will be time for questions. So let's start with the overview of DDT. DDT was originally produced by a company called Alinea. Later it was purchased by ROCm company, and now it's owned by Linaro. It is a powerful commercial debugger specifically designed for HPC, but it can also do any kinds of debugging. It can debug serial, multi-threaded, MPI, GPU, including NVIDIA and AMD GPU codes, and very importantly, any combinations of the above. SharkNet had DDT for a long time, since 2007 or so. For a long time, it only worked with compiled languages, C, C++, Fortran. But relatively recently, Python support was added. And because it's fairly recent addition, it's still a bit lagging in terms of the features supported. But the support is improving rapidly. And that's why it's highly advisable if you are a Python user to use the most up-to-date version of DDT, and more about that later. DDT has all the basic features any debugger needs, including ability to play, pause, step through lines of your code, setting up breakpoints, watch points, trace points, ability to display added values of variables, memory debugging, and it has much more. A lot of DDT functionality is designed to deal with parallel codes. For example, there is an easy access to any MPI process or thread on CPUs or GPUs. You can control the execution of processes or threads either in groups or individually. One can visualize ongoing MPI communications. You can display the values of variables across MPI ranks or threads, and there are many more other features not listed here. A very short overview of DDT capabilities is on our own documentation wiki page. This is the first link listed here. But if you need up-to-date user guide with up-to-date detailed information, please consult the official user guide in the second link listed here. So let's start by discussing how to use DDT on national systems. I already mentioned DDT is a commercial software, and it is individually purchased and maintained by different consortia within Alliance. At this point, only 2 consortia have the license. This is SharkNet operating it on Graham cluster and SciNet operating on Niagara cluster. On Graham cluster specifically, there are a bunch of different modules you can load, but I'll only list those of interest. You don't really care about older version of DDT. So what we have is DDT-CPU flavors. These modules are only for DDT license, which can only work with CPU cores. It doesn't work with GPUs. We have the most up-to-date version 23.1.1. The license only covers up to 64 CPU cores across all the users at any given time on Graham. And it's available only under new standard environment 2023. This is not default yet, but it's already available. So you can already load it. If you need to use the most up-to-date version of DDT, you have to load it first. Comes April, it will become the default environment for everyone. We also maintain older version, DDT-CPU/22.01. Why? Because roughly 1 year ago, we realized we don't get much usage, so we downsized our license substantially. So we used to have 512 CPU cores, and we downsized to 64. So it is still perfectly usable, We have perpetual use license. The only thing we cannot update it anymore. So if you change dramatically operational system, this will stop working. But for now, my advice is if you really need the most up-to-date version of DDT, for example, if you're a Python user, you probably should be using the up-to-date 23 version of DDT. For all other users, you probably should be using a slightly older version. It's maybe a bit more than 1 year older version, 22, because it would allow you to debug much larger parallel codes, and you have much less chance of running into a situation where there are no licenses available. For GPU debugging, we have a separate license. It hasn't been downsized. It's been always at 8 GPUs across all the users. And to use it, you need to load the new environment, standard environment 2023, and then you can load DDT-GPU module. On Niagara, there is no GPU, so there is no GPU license on Niagara, only the CPU one, and only the up-to-date one, which is working with up to 64 CPU cores, similar to new license under Graham. So another important aspect about DDT, it's a GUI application, a graphical user interface. So there are two major ways how one can run GUI application remotely on a cluster. I will primarily focus on the easiest one. It's so-called X11 forwarding. But I will also briefly mention the other one, VNC. You need VNC for a couple of reasons. First, if your internet connection is not particularly fast, so it may be a bit laggy to use X11 forwarding. And second, there is at least one feature in DDT, which is a multidimensional array visualization. It's using OpenGL. It doesn't really work with X11, so one has to use VNC instead. So focusing for now on X11 forwarding, what you need to do, you need to have X Windows server running on your computer. If you're a Windows user, we highly recommend installing free Mobaxterm software. It has SSH client, X Windows server, and many other things. And X Windows server is enabled by default, so you don't really have to do anything. If you're a Mac user, install free application X Quartz. If you're a Linux user, you don't need to install anything. Everything you need is already there. You'll notice today I'll be mostly using salloc command to allocate compute nodes. Salloc allows one to allocate interactive nodes, and this is makes most sense when you debug, because debugging is very interactive process. For those situations when salloc is not sufficient, I will be giving some tips and hints at the end. How can you work around those limitations? So again, continuing discussing X11 forwarding scenario, here's the basic usage summary. 2 slides, actually, some. First, what you need to do on your terminal, like Mobaxterm, you execute SSH command to the cluster, in this case, Graham. You have to add -Y to enable X11 forwarding. And then you execute appropriate salloc command. For those who never use salloc command, it takes the same argument as batch command, our main command to submit jobs to the cluster. The only difference, you don't list them in a job script. Instead, you add them in the command line for salloc. Important point here, you have to add --X11 in all your salloc command to enable X11 forwarding. So now this forwarding works all the way from your computer all the way to compute node. Another point here, you have to add -g when you compile your code for debugging, with the exception of script languages like Python. And typically we compile with the optimization disabled, -O0, but it's entirely possible to debug optimized code. And in fact, many times, in many situations, you want to do that. For example, with 0 optimization, your debugging becomes quite slow, maybe much slower than optimized version of the code. So maybe unrealistic to get to the bug. And then you have to use the proper level optimization. Some bugs are optimization level specific. For those cases, you also have to use appropriate level optimization. The only disadvantage of debugging optimized codes is as you step through your code, it may become non-linear. It starts jumping back and forth. It can be a bit confusing, but it's still, you can operate debugger completely. It should be okay. At the end, you can use breakpoints and other ways to do more, a better way to navigate through your code. So it's totally doable. And then you load DDT-CPU or -GPU, depending on your situation. I also list, and the way you run DDT is simply say DDT space and then path to your code. Except for Python, I will show on the next slide. Python is slightly more complicated command, but MPI, serial, OpenMP, and CUDA, it's exactly the same way. You start the debugger. For CUDA, again, you choose appropriate SLOC arguments. In particular, here I'm requesting P100 GPU. And also I need to load CUDA module to be able to compile my code. Another important point for CUDA code debugging, you add -g and also -G. -g takes care of the symbolic information on the host side and -G on the GPU side. If you start a debugger and you do not see the source code in the main window of DDT, probably you forgot to include -g or maybe -g and -G if it's a GPU code. Now to Python debugging. As our command looks as before, you do need to load a corresponding Python module. And then the way you run it, you say DDT space Python or Python 3 space, then you paste and copy this special name. This is the variable name, and then path to your script. MPI Python debugging is possible with under MPI for Py module. So you have to load it first. And you add extra couple of commands here in your DDT command. You have to add MPI run -np and then choose number of ranks for MPI Python code debugging. And now just a few words about the alternative way of connecting. Instead of X11 forwarding, this is the VNC connection. You can find detailed information about VNC connection if you Google for VNC, Digital Research Alliance of Canada. It will bring you to the corresponding wiki page we have. So basic steps, you have to install Tiger VNC client only. It comes as client as a server. You only need client. And it's available on Windows, Mac, and Linux. It's a free application. And then you open your Tux terminal, for example, Mobaxterm under Windows. Log into cluster as usual. You don't have to use -X11 or -Y for this. Our wiki page gives you fairly complicated instructions. There are multiple steps you have to do to enable VNC connection all the way inside the compute node. To make your life much easier, I created a helper script. So I warmly recommend you to use the script. It's available on Graham and Niagara. It's inside my home directory. This is my home directory /bin/vnc. It's a bash script. We just execute it. What it does, you have to salloc first inside the compute node, and then you run the script, and then it will guide you. It will tell you to do a couple of steps to finalize this procedure. There is a fairly recent alternative to run VNC is by using Jupyter Hub on the cluster. Again, there is a dedicated wiki page. You can Google for Jupyter Hub, Digital Research Alliance of Canada. And specifically, you want the desktop option. This is the one you want to use under the Jupyter Hub. And that will run VNC internally on compute nodes. So it's just alternative way to using my script. All right. And the bulk of this presentation will be a live demonstration where I'll first cover basic features. And I will show you different kinds of codes one can debug with DDT. So for this, let me switch to Mobaxterm. I'm under Windows currently. And I already allocated nodes on Graham using salloc command with --X11. And the reason I did that, so to make sure these nodes are available, so I don't have to wait during my presentation. But normally, you just go back to the slides, the summary slides, and execute the appropriate salloc command. So the first tab on Mobaxterm, this is for serial or MPI code debugging. Inside my home directory, by the way, you can copy. Next time you log into cluster, you're welcome to copy the whole directory. It's inside /sym/ddt_2024. I made it readable, so anyone should be able to copy the whole directory. Now I'm inside this directory, and there are a few folders with different examples. So let me start with the serial code example. Each folder has a README file, just to remind me and remind you which steps need to be taken. in particular which SL command needs to be executed, then I think you would have to change the account name. You have to change to your own account name. For now, I'm using the default environment. For now, it is standard environment 2020. So when I say module load DDT-CPU without specifying the version, it will load the older version. Remember the older version, which has much larger license. This is the default DDT version under the old environment. When I start debugging, showing Python debugging, I will show you the alternative, how to access the most up-to-date version of DDT through newer environment. But for now, we'll be using slightly older version of DDT. And continuing with my instruction, I will compile my code. It's a simple serial C code, which deals with traveling salesman problem solving. And as you can see, I'm using -G-O0 to make it debugging friendly. I'm using Intel compile because it's default one in the old environment. New environment GCC is the default one, by the way. Okay, and DDT is loaded. It's 22, version 22. So all I need to do is say DDT space and then path to my binary. Under Mobex term, GUI applications are often launched minimized. Sometimes it's maximized, sometimes minimized. It's I don't know why it's doing that, but right now it's started maximized. But if it's minimized, just find the window down here and click on it to open it. This is the first window you'll see in all DDT launches. It will automatically detect whether it's MPI, OpenMP, CUDA. In this case, it's not. It's a pure serial code. Just briefly about memory debugging, I don't have time really to cover this feature. It is disabled by default. And the reason for that, when you enable it, debugging becomes typically slower. So only do that when you actually debug memory bugs, such as memory leaks. And go to details, and what you need to do, you have to choose which option applies to you, whether it's C Fortran no threads, C Fortran threads, C++ no threads, or C++ threads. And then you can use balance option, or you can change the level of aggressiveness. The more aggressive it is, the slower the debugging becomes. But I will not use for this presentation memory debug. So otherwise, all we need to do just to click run. So this is the main window of DDT. And so let me explain the main parts of this window. By the way, it's highly configurable. You can drag elements of this window around. You can add more windows, but the default window is very usable. So I will be just using the default one. So on the very left, you see this source code navigator. If your code consists from multiple files, it will list those files here. And also inside each file, it will list all the functions inside that file. And that allows you a single click access to any of the files and any of the functions of your source code. In this case, there is one file, two functions. So I click on the function, it brings me instantly in the middle window to that particular function. And there is also main function. The main window is in the middle. This is the source code. So if instead of source code, you see some error message, most likely you forgot to include -G or maybe -G for GPU code debugging. So you have to quit DDT, recompile your code with the proper flags, and then launch it again. As you can see, the syntax is highlighted, so it's quite readable, easy to read. And so next, let me show on the right side, there are a few tabs here. The default tab is current lines. What it does, it shows you the values of variables on the current line only. And only it shows local variables. It doesn't show global variables. More about that in a second. If you want to see values of variables across multiple lines, what you can do, you can use your mouse and with the left mouse click drag across multiple lines. And then you see those variables listed on the right. By the way, you may recognize some of the values are non-initialized yet. They have weird values. If you want to see all local variables, you switch to another tab. And that's why you can access all the local variables. So going back to current lines, sometimes or quite often, you need to see more things. I'm going to delete, there's some old information here. So here's the evaluate window. It's a very powerful window. So sometimes you want to monitor value of particular variable as you step through your code. How? I'll show in a second. And this window will not be useful because it only shows current line. And this tab is probably too much information. So what you can do, you can basically copy this variable to evaluate window. There are a few ways to do it. You can just click and drag it here. This is the simplest way. A more powerful way is to right click here, add expressions. So it's not just variables, you can add both local, global variables, and any valid expression, arithmetic expressions, Boolean expressions, etc. Reference, the reference of your pointers, it's all can be entered here, and it will be constantly monitored within the current context only, within the current function. So this is a very powerful way to use an evaluate window. Moving on, so back to the source window. How do we navigate? So initially you can see the highlighted line. This is the position of the debugger right now. It's paused on the very first executable line. To navigate through your code, there are a few different ways. The simplest is to use one of these green arrows. Either step over, step into, and sometimes step out. The difference between step into and step over is if you encounter a function, step into will step inside that function, and step over will keep you on the same level. It will not step inside that function. So let me just make a few steps here. And then I'll go inside this loop, and then you can see the problem here. It will probably take forever to go to the spot you need. So just stepping through your code is probably not enough for debugging your code. There are a few other ways to navigate more quickly through the code. In particular, if you right click on any line of the code, you can say run to here. This way overrides everything. I'll discuss in a second. Breakpoints, whatever you create, it's going to be overridden, and it takes you there if possible. Not all lines of code are accessible. As long as it's accessible, it will take you there. This is one way to navigate. But let's see this example. There is a huge, this is Monte Carlo's type of calculation. This loop is 100 million after iteration. What if the bug I'm encountering, I suspect, happens around iteration number, I don't know, 1 million. How to do that? By the way, this is old stuff left over. How do you get to the specific line of your code, and even more specifically, specific iteration of the loop? For that, you can use breakpoints. So the simplest way to create breakpoint is to hover your mouse here on the left, choose where you want it, the line where you want it to be paused. You click it here. You can also go to breakpoints. This is also a set of tabs here. Go to breakpoints, and now it's listed here. By default, such a breakpoint is unconditional, so there is no condition here. So what happens? You can navigate to breakpoints or between breakpoints by pressing this play button. It's like operating an MP3 player. You press it. You don't need breakpoints. You can press play, wait for a while, and then press pause, and then look around. It's going to end in some random points inside your code. Probably not very useful. With breakpoints, you specify where you want it to be paused, and then click play, and it will pause there. Okay, it's great, but this is a giant loop with k going over 100 million iteration, and we are at k is equals 0. By the way, let me drag it here. So it makes it clear the advantage of using evaluate window. So k is 0. So how to get to, let's say, 1 million iteration? I'm going back to breakpoint tabs. I double click on condition, and I use this current language syntax, whether it's C, Fortran, Python, etc., to enter the Boolean condition. In this case, my condition k equal is, let's say, 1 million. Then I hit enter. By the way, you can access all the breakpoint features if you right click here, say edit, and this might be more convenient interface to access all the features. For example, it can apply to specific thread or specific MPI rank. It can start on 0 pass or nth pass, and can be triggered every nth pass, and this is the stop criteria forever in this case. Here's the condition. So now, if I click the play button again. It may take a while because I chose 1 millionth iteration. Maybe it was a bad idea. So this is unoptimized version of the code, so it's quite slow. So let me pause. So I demonstrate another feature. You can pause anytime you want. And what I'm going to do, I'm going to change my condition. By the way, K became, as you can see, it's 89,000. So let me change to 100,000. You can only set breakpoints in the future. By the way, anytime you realize you passed the bug point, you need to restart your code. The way to do it, you go back to File, Restart Session, and then it will restart using all the parameters you chose initially, number of MPI ranks, number of threads, and all the rest of the parameters you chose in the original window. So in this case, in 100,000, I'm still haven't reached that point yet. I can press play. Now it should be more doable. And indeed, voila, we are at 100,000 iteration. What we can do here, and when you do conditional breakpoint, there is a tiny plus sign. You may or may not be able to see it next to my breakpoint. And then you can navigate step by step if you need to. Or you can create another breakpoint within this iteration. So you can navigate any way you like. You can create a bunch of breakpoints as needed. You can delete them if they're no longer needed. You just hit delete button, or you can just disable them by clicking here. They're disabled. It becomes gray, so you can still keep them for future debugging. Anytime you can come back and re-enable them. And if you quit debugger and then debug exactly the same binary name of the code, all these breakpoints will be remembered. Also, everything you enter in evaluate window will be remembered until you explicitly hit it and hit delete. Then it's going to be deleted. So there is also input-output tab, and all standard output goes here. You can also type things into standard input. There is also watch points tab, trace points tab. More about that later in the advanced part of my presentation. Stacks tab will become useful or more useful when we discuss parallel code debugging. So we should be getting there very soon. So I'm done with the C code debugging example. I'm going to quit my window. And now I'll briefly show you Python code debugging. Again, I will consult my README file. So for this, I really need to load standard environment 2023. So I will just execute this whole command. And also, I need some other modules for my Python codes already created in environments. I just need to activate my environment. And I have instruction inside this folder if you need to do it yourself. All right, so now I'm ready to debug serial Python code. I'm just going to use these instructions. So as I noted before, you need to add Python 3 and also this special environment variable. It looks a bit slow when I start DDT, but when you use VNC connection, it's typically much snappier. So in this case, it started minimize. So go figure. Sometimes it's maximize, sometimes minimize. In this case, it's nothing to change here. I just click run. And then you will see a familiar interface. There are slight differences. For example, you see many more other functions, not just your own code, but some other functions. Also, all variables are listed here, separate entries. This is a Python thing. But otherwise, it's same idea. You can create breakpoints. You can say right-click, run to here. You can create breakpoint and press pause, play and then pause if needed. And then you can step one by one, line by line. And as before, you can highlight multiple lines to see their values, or can go locals. And again, you can use the add expression in the evaluate window. This is breakpoints. Watch points are not supported yet under Python. Hopefully it's coming in the future. But most of basic functionality is already working well with Python, so you're highly recommended to use our DDT to debug your Python code. So now switching to MPI codes. Let's give you a first example of a parallel code. It's MPI C code. I'm still good with my salloc. I allocated 8 ranks, so 8 CPU cores, so I can also use it for MPI code debugging. And in this case, I will be compiling this deadlock file. And as the name suggests, this MPI code has a deadlock bug. Deadlock, it's a kind of bug when you run your code and it's hanging on one particular line of your code. And I will demonstrate in a second. There is a bit of a caveat. There is a bug in our OpenMP library, which prevents one feature of DDT, specifically visualization of MPI communication. Only when you're dealing with deadlocks and MPI, you should be doing this. Before you run DDT, you have to execute this export command. It's listed on our wiki page for DDT. And now I can run my MPI code under DDT as before. So as you notice, I didn't have to use MPI run here. It's taken care of by DDT itself. Now it's the first window you see. Now MPI was detected, so you don't have to do anything. All you need to do is to choose number of ranks you want to use, and then you click run. It may take a bit longer to connect to all the ranks. In this case, it's 8. So interface looks very similar to what you saw before with the serial code, with one important addition. There is a new bar. This is a rank navigator. It allows you with a single click, mouse click, to go to inside any rank of your MPI code. Initially, all ranks start simultaneously. They're in sync, and they're all on the very first executable line of my MPI code. So what I can do, for example, I can right click, run to here. It still works under MPI. And for MPI, it has extra feature. It will try to synchronize as many ranks as possible. It's not always possible to bring all your ranks in sync and bring to a particular line of the code, but it will try its best. And the way you can see which one synchronized, which one not, this kind of orangey color, which means all ranks are paused. They're properly on this particular line of code. If any of them are green at this point, they couldn't reach that point. They're hanging somewhere. So what we can do here, pay attention on the right. So now you see there is an interesting thing going on with the little pictograms next to our variables. So what it does, it shows the distribution of values of this particular variable across all the ranks. It's just a simple visual representation. It's not precise, just to give you an idea. So this seems to be constant across ranks, and this seems to be variable. More detailed information can be obtained by right-clicking on a variable name, and then you say compare across processes. For OpenMP code, you would choose across threads. And now it gives you all the information you ever need. It gives you the actual values. These are the ranks. These are the values. And it gives you all kinds of statistics. Number of ranks, sum, mean, max, mean, variance, number of incorrect, wrong values, also negative, positive, and 0 values. You can also export, save it as CSV file for further analysis. And yeah, this is quite powerful way to look at variables in MPI code. So what I'm going to show next is breakpoints work as usual. So you can create any breakpoints you want. By default, it will work for any rank encountering this particular line of the code, but you can make it rank specific. So if you create a breakpoint, you can, the way you do it, you can right click, add it, and then you say which process. And also process group. By the way, it's a very useful feature. I'm going to tell you about it next. So by default, the only bar you see here is all. So what you can do with this, it's a group. This is the only group available by default, it's all. In my default focus is on the group, which means every time I click next, it will try to operate all my ranks synchronously. And as long as it's possible, it will keep them sync, as is the case here. But sometimes you want to operate individual processes. For this, you have to switch your focus to process. Now you switch to a particular rank you want to operate, let's say rank 6. And then you can operate it individually. So you can step through the code and then you go back to other ranks. You see they're still on the original line, only rank 6 in a different line. If you switch focus back on group, you will see there are two highlighted lines. One is the current rank line, and any other lines you will see this corresponds to other ranks, wherever they happen to be. For this, it's also very useful to use stacks for parallel code. Now, once your execution becomes diverse, there are different ranks on different parts of lines of your code. You will see multiple lines here. By hovering the mouse on each of these lines, you will see which particular rank is on this particular line and this particular function. And it's a very easy navigation mechanism. If you click on any of this line, it brings you to that particular function, that particular line, and that particular rank. So going back, this brings back to my rank 6. So it's very easy navigation. With MPI codes, it's often useful to work with groups, custom design groups. For example, in MPI codes, very often you have 0 rank is special meaning, let's call it master rank, and the rest may be worker ranks. You can create custom groups easily. There are a few ways to do that. I'll show you one. You just click on one or multiple. If you need to highlight multiple ranks, you hold your Control under Windows, Control, and then you choose any number. Or if you press Shift, it will enclose all the ranks enclosed here. In this case, I want to create master, so only 1, 0. And then I'm going to right-click, create group. And I'm going to click clear root. You can always rename that. Let's say it's master. And then I click, and then shift click here, right click here, and create another group. And this is another user defined, and let's call them workers. What you can do now, you can click, so pay attention, this should be focused on the current group. And if you click on any of these custom groups, you can operate them together. So let's say master can move master a few steps, and then I go to workers. Workers, by the way, they're already out of sync. Remember, I moved 6 rank, it's away. So that's why you see 2 highlighted windows. And when focused on the group, it will try all of them synchronously, keeping the same distance between each other, as long as it's possible. So you can still see there are 2 highlighted. They're still offset. So it tries to maintain offset. So it can be quite useful to operate custom design groups. When you don't need them, you just right-click, you delete group, and I'm going to do that for that group as well. There are many other ways to create groups. For example, groups can be based, sorry, I pressed the wrong one. Groups can be based on which ranks happen to be on this line of the code. You just right-click here, and new group, for example. So there are many, many ways to create groups. A very powerful mechanism. And finally, I want to show the deadlock visualization. To deal with deadlocks, I'm going to remove this breakpoint. I press play, and I wait, so everything is green. So I press pause. So I'm on this line of the code, and there is no more standard output. I press play again, I wait again, pause. It's still there. So it's already suggestive this is some kind of deadlock situation. But DDT has a powerful feature. You can go to Tools and Message Queues. And reminder, for this feature to work, you need to execute the export command I showed a bit earlier. Otherwise, you will not see this useful window. I did execute export command, so I actually see the ongoing MPI communications. Show diagram key tells me the meaning of the color. So red means send. And as you can see, this is the ring topology here. And all the ranks apparently trying to send something, but dash 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 part means the recipient is not ready to receive, the classical deadlock situation. How to solve deadlocks in MPI? It's a separate subject. There are at least 5 or 6 different ways to fix this bug here. My favorite one is to switch from blocking communication, send, receive, to non-blocking, I send, I receive. And that takes care of this deadlock. So that's all I wanted to say about MPI debugging. I don't think I have time to show Python MPI debugging. It looks pretty much exactly the same as regular MPI debugging. I need to go to OpenMP. So I'm going inside another allocation. This allocation was specifically for multi-threaded codes. So what I need to do here, modulo DDT-CPU. I'm going to compile my OpenMP example. Same rules -G-O0, but also -F OpenMP if you're using GCC. And then you run debugger as before. So again, if you use VNC, this is much snappier. This is going to be much faster. It detected correctly, it's OpenMP. I just have to choose number of threads. I click run. It looks very similar to a previous example. There is a caveat. First of all, there is extra bar, it's threads bar. But in OpenMP, unlike MPI, initially there is only one thread, the master thread. To be able to see all of the threads, the team of threads, you have to be inside a parallel region. And the tricky part is you can't just step into a parallel region. It's not going to work for whatever reason, whether it's OpenMP limitation or DDT, I'm not sure. But you can navigate using other methods like run to here, or best of all is to put a breakpoint here. So I create a breakpoint, then I press play. Now you can see that all 8 ranks here. Okay, and what you can do, you can compare across threads. It's going to be similar to comparing across MPI. And by the way, this is how vectors look like, or arrays. They are compacted, but you can open them up, look their values. And if it's 2 or multidimensional, what you can do, only if using VNC connection, not X11. For you right-click on the value of the variable. In this case, it's A. And what you do, you can say view array. So I don't want to do actually under X11. It will be super slow. And first thing to do here, you click evaluate. You choose correct array expression. It's usually chosen correctly, the correct range of your indexes. You click evaluate, and it will give all the values. I hope it's, oh no, it's not too slow. And then, for example, I can export. All the values can be exported as a CSV file to be analyzed in another software. There is also statistics. It's very convenient for large arrays or vectors. It tells a number of incorrect values, also standard deviation, etc. So that's it about OpenMP debugging. And my final, probably the final example is CUDA debugging. Also, the DDT-GPU module we have does work with AMD GPUs, ROCm heap, but we don't have any AMD GPUs readily available for this presentation. We might have them in the future, but for now you can just take my word. AMD GPU debugging will look very, very similar to CUDA debugging. So I'm going to go inside the same directory and inside CUDA. So I will only show you the CUDA debugging part. I already allocated with one P100 GPU. I will be using the most up-to-date version of DDT-GPU with newest environment. Also, CUDA model is loaded here. And I compiled with nvcc command. It's a reduction, simple reduction example. And then I debug it as usual. So I have to open it. It's minimized. It correctly detected CUDA, so all I have to do is click run. Somewhat similar to OpenMP. Initially, you see only one thread. And to navigate inside the GPU function, a kernel or device function, you have to click on that particular function. And I already created a breakpoint. So the best way is just to create a breakpoint, and then you click play. It will take you inside that particular kernel on that particular line of the code. As you can see, the execution state, we paused right now, but it's all over the place. There are a bunch of different GPU threads all over the place. You need to go back to this stacks tab to see where our different threads are. You can hover the mouse and it tells you which particular threads are. I don't know why it's not working. Yeah, something happened. Normally it shows you which particular threads are on that line. And as you can see, you can click to different lines and it takes you to different. Here's the bar, navigation bar between different GPU threads. You can ignore the CPU threads. This is all system level. There are no actual CPU threads used in this example on the GPU thread. So you can choose the block, whatever block you want to go to. You can choose whatever thread you want to go to. And this tells you a hint what is the grid size or the block size. And then you hit go. It will take you inside that particular block and thread. One caveat with GPU debugging, GPU has very limited resources compared to CPU for debugging specifically. And GPU debugger is very, very forgetful. You have to be basically to be on that particular line of the code, execution part where it's actual execution taking place, to be able to see the values of variables. If you go anywhere else, chances are you will not see those variables. Some of them are visible, most of them will not be visible. So it's tricky. You really need to get to that particular line to explore the values of the variables. And as I mentioned, this is because of limited resources. GPU just doesn't have resources to keep all those historic values of variables. And I think that's I wanted to show with the GPU code. I also have an example of hybrid code, CUDA/MPI, but I do not have time for that. I still have to go through a few of my remaining slides. So let's get back to the slides. Advanced feature. So what I didn't discuss, watch points. Unlike breakpoints, which are line specific, watch points are line agnostic, but they are variable specific. They can be very useful if, for example, something bad happens to a particular variable inside your function. You don't know where exactly. You can set up a watch point and it can watch for updates, edits, or even reads. Any reads or writes or both will be monitored. And when you press play button, it will pause next time this action happens to the variable. Trace points is somewhat more technical. It's more useful when you do offline debugging. I'll discuss that in a second. What if salloc is still limiting for you, or you wait forever, salloc never starts? You can use some other tips and tricks to avoid this limitation. For example, if the bug is encountered at a predictable point, most software allow you to write a checkpointing file. So make sure the checkpointing file is written right before your bug, and then you can run DDT interactively using salloc from that checkpoint on, and then it should be much sooner to get to your bug. But what if it doesn't work? For example, the bug you encounter happens at random point, or you have to wait forever for it to happen, or if you need more resources, then you can allocate with salloc. Another trick you can do for these situations, advanced feature attaching to already running program. I have instructions here. I don't have time to do live demonstration, but basically the way to do it, you submit your job via SBatch. It's like regular non-interactive job submission. Once it's running, you use sq command to find out which nodes are used by the job. Then you launch DDT on the login node without any argument. And then there is advanced option attached to an already running program. You click choose host button, and then you manually type in the nodes which you know your job is using. And then DDT will automatically detect all the processes, and you can start. It will show you the current state of the job. I believe when it happens, your job will be put in a pause. So it will try to pause it. So you will see the pause state of your job. You can step through the code for a while. Then you can kill DDT and then do it again next day, for example, if it's a large code. So this is a useful workaround. Another workaround, if your code crashes, producing large core files. So as long as the code was compiled with -G, it has the symbolic information. What you do, you launch DDT on a login node, and there is an advanced option there. You can choose core file to analyze, and then you basically you will see the state of your code at the moment of the crash. And in many cases, that should be including the values of the variable, for example, on that line of the code. In many cases, that should be sufficient to figure out what happened. There is also offline debugging option, not particularly recommended, kind of awkward. Debugging is very much interactive process, but in principle, you can submit as batch job with this line, DDT. Make sure you load module, load DDT-CPU or GPU, and then you say DDT-offline-n if it's an MPI code. You can say snapshot interval every 10 minutes. It will dump all the local variables to a file. There is also a way to add trace points, so specific variables, a specific line of the code can be recorded. But it's not particularly useful way to do debugging. So we reached the end of the presentation. You can contact me directly after this presentation at syam@sharknet.ca. You're welcome to send also email to our ticketing system at help@sharknet.ca or support@alliancecant.ca. Thank you very much for your attention.